How do you calculate standard molar entropy? Have you ever wondered how scientists measure the disorder in a substance? Today, we will look at how to calculate standard molar entropy, a key concept in thermodynamics. Standard molar entropy, often represented as S with a degree symbol, is the entropy of 1 mole of a pure substance at standard conditions. These conditions usually mean a pressure of 1 bar and a temperature of 298 Kelvin, which is 25 degrees Celsius. The units for this measurement are joules per mole per Kelvin. Unlike enthalpy, which can vary, standard molar entropy values are absolute. This means that even elements in their standard states have definite, non-zero entropy values at room temperature. To calculate the standard molar entropy of a substance, we start from absolute zero, which is 0 Kelvin. The process involves heating the substance and measuring the total entropy gained along the way. First, we heat the pure solid from 0 Kelvin to its melting point. During this stage, we account for the heat capacity of the solid. Next, we add the entropy change that occurs during melting, known as the latent heat of fusion. After the solid has melted, we then heat the resulting liquid from its melting point to its boiling point, again considering its heat capacity. Once we reach the boiling point, we add the entropy change due to vaporization, which is the latent heat of vaporization. Finally, we heat the gas from the boiling point to the final temperature, often to 198 Kelvin, using the heat capacity of the gas phase. Mathematically, we can express this process as follows. The standard molar entropy equals the integral of heat capacity over temperature for the solid, plus the entropy change from melting, plus the integral of heat capacity over temperature for the liquid, plus the entropy change from vaporization, plus the integral of heat capacity over temperature for the gas. The entropy changes from melting and vaporization are calculated by dividing the latent heats by the temperatures at which these phase changes occur. This method aligns with the third law of thermodynamics, which states that the entropy of a perfect crystal at absolute zero is 0. In practical terms, you will often find standard molar entropy values in thermodynamic tables for many substances. This saves time and effort, as calculating them from scratch can be complex. These values are essential for predicting the spontaneity of chemical reactions and understanding the randomness in a system. So, to sum it up, calculating standard molar entropy involves integrating heat capacities over temperature ranges and adding contributions from phase changes. This method connects the concept of entropy to measurable heat and phase data, making it easier to grasp.